Okay, so for this part, we're going to start with implementing the float2, and then we're going to implement the camera. So we're just going to have a camera that's going to be able to move in the end, and we're going to implement our rays. So we're going to see exactly what a ray will actually consist of. So we're going to start with the float2, which is going to be, I promise, very simple. So it will start with this same thing. Again, we're going to say float2, kt. I don't think you have to type the kt, but it doesn't matter. So it's going to be very similar to the float3, but a lot simpler. So first of all, we're going to start with our x, which is going to be a float in our constructor, and y, which is also a float. Okay. So again, we're going to define operators. And for these operators, we're going to just very quickly, we're going to have basically the same ones. So if I go here, I'm going to define all of these as they're here. And so I'll just copy them here. And the difference is that I obviously have a float2 here. You could obviously write them from the beginning, but really no reason to do this. In fact, I will select all of these and I can just press Control F, or that's not what this is inside the, yes. And I can say float3. Oh, well, that didn't work as intended. So there's a button for selection here. He said, is it here? Who knows? So it doesn't matter. So anywhere we have float3, we're going to replace it with a float2. So replace these. Perfect. And obviously we don't have a z. So z goes bye-bye everywhere. And that's it. So there's going to be a lot less things here. And here we're going to move on by adding a plus, minus, times, and everything. So everything we had here. So it's basically these things. So again, very easily, I'm just going to copy paste them. And again, the difference is that I'm going to take every float3 and I'm going to make it a float2. And this is not needed. So we remove the last component because we don't have a z. Okay. And that should be okay. Cool. That's it. We probably won't touch this ever again. So I'm going to close the float2 for now. And I'm going to go to, let's go to the camera. So we're going to start with a very simple camera implementation. So we're going to say camera.kt. And well, in our case, our camera, well, we're going to have inputs of the camera, so we can actually move it. But for now, we're going to start with just a simple camera that is a simple position. And we're going to see what a camera is actually made out of. So the first thing that we want is to know where the camera is. So this camera is going to store something called a position. So it's going to be the camera, I'll say position. And obviously that's going to be a three-dimensional, a point in a three-dimensional space. So we do have to, we need a float3, which is nice because we just made it. So because of our float3 implementation, we can say float3, and that's it. The next thing is going to be a direction. So we know where the camera is positioned in the world. We need to know where it is pointing at. So we're going to say camera direction, which is also float3. In this case, this is going to be a normalized float3, but it doesn't matter for now. The other thing we can define is how big the screen width and the screen height is. So we can say val. The difference between var and val, by the way, var is a variable, so it considers it something that can change. Val is something that when you give it a value, that's it. It will never change. It's a constant, basically. So we're going to have, again, our screen width, which is a float. not a float, an int, and our screen height, which is also going to be an int. And that's it. That's our camera. So before we go, we're not going to go into any inputs right now, but there's a few other parameters that will be needed to use the camera. So if you think of a camera, you have a point, like an eye, where it starts from, and then it essentially is an eye that looks towards the direction, and towards that direction it creates a bit further away from the eye a rectangle, and that's the viewport basically. So to describe that, because we're going to need that to generate the rays, we need a few things. The first one is the aspect. So it's essentially the aspect ratio of the camera, and what that is, very simply, because we have a screen width and a screen height, that is literally screen height or width to float just in case. Because Kotlin does weird things if you don't do these like explicit castings. Then we say height, we say to float. So this is our aspect. Then the next thing to describe the camera is, so we talked about rectangle. So, okay, well, we need, so essentially what we will be doing is, if we consider an eye being my eyes or my position, right now as I'm looking at my monitor, this will be the camera position. The direction will be the same thing. So it will be where I'm looking, right? And let's say that the monitor of my computer is constantly attached to me. So when I move my head around, it moves with me. So in order to create the image on the monitor, which is going to be what I'm going to be seeing, I have the monitor, which is a rectangle. And this is what we're describing. So in order to describe a rectangle, we need three things, because it's not a square. So we need three of its corners. So we're going to start with the top left corner. So we're going to say top left, which is again flow3, which is nice. You can see why we implemented this. We're going to see it literally everywhere. And we're going to make a flow3 that is minus the aspect ratio on the x-axis, 1.0f on the y-axis, and 0.0f on the z. So this is going to be the top left. Now we want to describe the top right. That's a flow3 again. Again, flow3. Now, this is going to be obviously x-axis aspect. And then we're going to have our floats. Keep in mind, these are the initial values. So you're going to see what we're talking about a bit later. And 0.0f. These will not change, but they won't have to. What is it not like here? Oh, could be private. Doesn't matter. Finally, we want a bottom corner as well. So we're going to say bottom left. Again, a flow3. And this one is going to be very simply minus the aspect, because it's left. And -1 this time. And 0.0f. So z will always be 0. And you can kind of see if you imagine the corner, right? You have left one is minus on the x-axis. Right one is plus. And when it's up, so it's a top corner, it's 1 on the y-axis. When it's a bottom corner, it's -1. So you can see how that's created. Okay. And believe it or not, that's all we need for now. We're going to implement another function after we create the ray class. Now, I am using classes because Kotlin does not have structs. So, yes. Unfortunately. So, we move on to rays. And finally, we've reached the point where we're creating rays. Okay. I have, by the way, added everything on a Git. Not GitHub, but I've just added it to a Git. So just for version control purposes, but you don't need to do this. So let's start our rays. So I found this picture on the internet, as they say, and this kind of points out what exactly we're trying to do. So we have the camera origin, or the camera position in our case, and it's casting rays from this origin on directions based on the pixels on the plane. So if the plane is my monitor, then it goes, okay, well, the pixel is there, this pixel is there, this pixel is there, this pixel is there. If I take a ray from here, or a vector from here to here, what is that direction? And basically that's how we will be doing this as well. So our position will be this, but our direction of the ray is going to be based on where the pixel is. And then we see whether that ray misses. So if we have a sphere like here in the world, basically we check whether we hit this sphere or whether we miss it. And believe it or not, that's ray tracing. So based on what you hit something, on what you hit, what its material is, what its properties are, you just move on. You color the ray, you color the pixel, that's it. So ultimately what we want to do is we have a primary ray. That's what this is called. So a camera ray is a primary ray. We're only for now going to be using primary rays. And this primary ray will try to hit something to color the pixel. If it hits something, it's going to color the pixel appropriately. So if it's cast from this pixel, then and it hits it, it's going to be colored, for example, whatever this color of the sphere is. If it misses it, like this ray, it's going to be, doesn't matter, it might be a skybox. In our case, we're going to have an HDRI image. So we're going to have a sky image, but we're going to be doing this later. For now, we're going to turn it to black. So basically, it's just going to be a black color. Okay, let's start creating our ray. So our ray is going to be tiny, just to see how simple rays actually are. So again, I said last time that our ray needs to be made out of a few things. So the first one is the origin. So we're going to have, obviously, everything's a float 3. So this one is going to be called O. So that's capital O for origin. Then D. So capital D for direction, which is going to be normalized always. And that's it for the constructor. Inside, however, we need a few other things. The first thing is, well, okay, we have a origin, we have direction. We want to have a length of array. So we want to have a distance. For the beginning, the distance is going to be considered infinite. So basically that means that we can hit anything in the scene. The reason why we're keeping a distance is we need to know what we don't need to know whether we hit something most of the time. We need to know what was the closest thing we hit, because imagine you might have a sphere and then behind that sphere there's another sphere. And for whatever reason in your implementations, you hit the sphere that's furthest. You don't want to color that one. You want to color the one that is in front of you. So yeah. So we're going to have here a var. It's going to be called T. And it's going to be a float. And it's going to be 130f, which is almost infinite, basically. So a very large number. So 1 to the power of 30. Or 10 to the power of 30. Okay. So we have this. What else do we need? Well, we will have, especially in a scene where we have a lot of objects, we're going to have, or primitives, we're going to have IDs for each of them. So we have 3 spheres. We're going to have sphere 1, 2, 3, so 0, 1, 2. And we want to have an ID on each of these to know which one we hit. So we're also going to be storing that. So we're going to be saying object index. That's going to be a simple int. Normally, this could be an unsigned int, but don't do this in Kotlin. So it's just going to be -1, which means we didn't hit anything. So basically, if t is this, or object IDX is -1, that means that our array didn't hit anything. And finally, we're going to have one more variable that's going to be called inside that we're not going to use yet. And that's going to be a Boolean, and it's going to be false. So what is this variable? If we use, which we're not going to be doing perhaps for this tutorial, we might be doing it at the end, but we're not going to be doing dielectric materials, so like glass materials. So for example, if you have a sphere that's glass, your ray will hit the sphere, and then you're going to need another ray to go inside the sphere. You need to know whether you're inside the sphere or not, because you need that information. We're not going to use it for now, but we're going to keep it here just for the purposes of if we need it. Finally, we're just going to have a helper function called intersection point. So if we hit a sphere or we hit a triangle or any primitive shape, we need to know where we hit it. That is where we hit it in the world. So if we want to have that, we want to get this information very quickly, we might as well use a function that gives us this information. And you might already be imagining what that actually is. Because very simply, all we're returning is, well, I hit something, well, I started from an origin, so that's O. And okay, that's where I started. And I'm going towards direction D, which is right here. And it's also normalized, so it doesn't add to any magnitude. And, well, I'm going towards D for distance T. And that's it. So basically you start from O and you go for distance T towards direction D. And that's how you find the intersection point. And that's it. So now we're going to go back to our camera and add something very important. So the camera needs to be able to generate a primary ray. We already said the primary rays are the rays that come from the camera, right? So we need a function. It's going to be called generate, let's say, primary ray. So that's going to be for a single one. And it's going to have two parameters, x and y. And obviously these are going to be our pixels. And they're going to be floats for a few reasons. And that returns array. So this will use the x and y pixels, the current pixels. We're going to use a for statement or two for statements to go through these pixels on our screen. And for each pixel, this will go into the camera and generate a primary array and return it. So the first thing we want is, and I'm going to be writing it here because it's nice to have it. We want to know what the pixel position is in the screen plane. So if I am talking about my monitor being the screen plane, what is the pixel position on it? So those we're going to call, because they use a lot in graphics, U and V. So we go from coordinates X and Y to U and V. So we start with U. And that's also a float, we might as well say it. And in this case, it's going to be X times 1.0 F over the screen width. And that's how we get this coordinate. For V, it's very similar. It's Y times 1.0 F over the screen height. And that's it. So this will give us the UV coordinates that we want. The next step is to find what the point is in that. So we saw before that we need to know in the 3D world where point P is, right? Also, I'm going to turn this into var because these are going to be changing when we have inputs. So we need to know in a 3D world where this part of the screen plane is. So we're going to say val P, that is going to be that point that we're talking about. That is where the pixel actually is. And to find that, we use the parameters of the camera, or the properties of the camera. So the first thing that we need is we need to start from the top left. And then what we need to do is we need the distance between top right and top left. So we say top right minus top left. That is going to be multiplied by our u coordinate. And then to this, we add the distance bottom left minus top left. So now we're talking about the v coordinate. So now this is the vertical. And this will give us the point on that plane, which is nice. Then the next thing that we want is we need a vector that goes from our origin point, which is the camera position, is this thing here. And it goes towards point P. And basic math, you know what that is. I'm going to call it PC. And very, very simply, it's going to be P minus camera position. And, well, that makes sense, right? We want a vector that goes from camera position, from point A to point B. That's going to be B minus A. And that's what this is. Very simple. Now, the one thing we need to remember here is this needs to be normalized, because currently it is not going to be. What that means is we don't need the magnitude of this vector. Because we don't need the magnitude of this vector, it is very, very important. By the way, these are all flow threes. It is very important that we normalize it. So we had our function that we created in the previous one, and we can say this, normalize, and that's it. It's normalized. Nice and simple. Finally, we need to return that new thing that we created. So we return an array. So we're going to construct array here. And so again, the constructor of the array that we just created is going to be origin and direction. Our origin is obviously going to be, like we talked about before, it's going to be our camera position, or our eye in the world. And then our direction is going to be the PC vector that we just created. And that's it. So this will be able to generate primary arrays for any pixel that we give it. Perfect. So let's see how we do this here. Or actually, let's do it in the next one so we can actually kind of see what a ray trace scene will actually look like.